Hello dear students, welcome you all. In this lecture, I am going to discuss about the sample and hold amplifier, right? Sample and hold. You can see here that there are two words, sample and hold, right? And then we have amplifier. So, it means we are going to discuss about a circuit that is going to take the samples. Clear? That is going to take samples of what? Samples of a particular signal. For example, let this is a signal. Then this circuit will take the samples of this signal. Now hold. Hold means this will hold these samples for a particular time, and amplifier means we are going to use a amplifier in this circuit also. Obviously, it will be a operational amplifier, right? In total, I can say that this is a circuit that use operational amplifier to take the samples of a analog signal or a time varying signal, continuously time varying signal, and then it is capable of converting that signal into its corresponding digital format. We might have seen when we have discussed analog to digital converters that sample and hold circuit is a very important part in all those A to D converters. It is capable of converting analog signals to digital signals, and it is also capable of converting digital signals to analog. It is also used there, right? So here in this lecture we are going to discuss about this sample and hold circuit, and I can say sample and hold amplifier. After the discussion, the things will become very clear that how this circuit takes the sample and what is the meaning of holding, right? So I'm showing you the circuit diagram here. You can see here, this is the circuit diagram shown here, right? Uh, so yes, you can see here, this is the entire circuit, sample and hold practical circuit, right? Now you can see this is what? This is a operational amplifier, op amp. As I told you that this circuit is going to make the use of a amplifier, and obviously it is operational amplifier, right? Operational amplifier here used is, it is a voltage follower. We know from the theory of op amps that this circuit is voltage follower. The inverting input is connected with the output, whereas the non-inverting input is connected to the resistor and then to the capacitor. Means the incoming signal is applied across a non-inverting input of the op amp. This is supply voltage plus VCC minus VEE, right? Plus minus 15 volt, and these are the other terminals of the operational amplifier. They are not used, we have seen, although there is no need to draw these terminals here, but they have been drawn, so ignore these terminal 1 and 5, right? Then it is the load resistor, then it is virtual ground, and then we have connected a oscilloscope, CRO, at the input and at the output, right? Now we will apply a particular waveform. You can say we will apply a sine wave, right, at the input, right, and then we will look at the output. So one terminal, this terminal of the CRO is connected to the this signal, right here. It is given not signal, but this element of the circuit, and then it is also taken to the this, right, and then it is taken to the ground, right, whereas this terminal is here taken to the ground, right, and it is also connected to this. So this is the connection of a CRO, right. This is just for visualizing the input signal and output signal, that how input signal, if I take it a sine wave, then how this sine wave is converted into corresponding sample and hold waveform. We can say a kind of digital waveform, right. Now what is this? You can see here, this is what? This is N channel enhancement MOSFET. We have seen, what are the, N channel and P channel MOSFET, and what are the different types of MOSFET, right? So it is enhancement type of MOSFET here that we are going to use. This is source and this is a drain, right? This is gate, right? So you can see here the gate of the MOSFET is connected with the control pulse, right? That is usually of 1 kilohertz and 12 volt has its amplitude, right? It is connected at this, right? And it is a, a kind of a square wave, yeah, this format, right? This is what, this is capacitor of value 0.1 microfarad. It is connected here. This is a resistance, and then this further is connected to this here, right? Now, how this circuit will work, right? We know when the gate of this N channel enhancement MOSFET is applied with the positive pulse, right? In this case, this MOSFET will behave like a closed switch. Closed switch means the current will start flowing either from source to drain or drain to source, depending upon the potential applied here and here, right? But when the gate is at zero potential or it is at negative potential, in that case this MOSFET will behave like a open switch. It means it will not conduct anymore, right? So we can say it will conduct only during this positive part of this square wave, right? So whatever input signal is applied here, this signal will go to this MOSFET, and then after, when this gate is open and this MOSFET is behaving like a closed switch, then that time this entire signal will go to the capacitor, and the capacitor will start charging to that voltage, right? It will continue charging, right? It will charge, and then after, you can see here the negative cycle, we can say, or zero potential will reach at the gate, right? If I take this reference as 0 and this as plus, you can say then the gate will become zero potential. Now in this case, as I said earlier, this MOSFET will behave like a open switch. Open switch means now it is not going to conduct, right, electric current. So the signal coming from here will not be passed toward this side, right? So during that time, what will be the effect on the capacitor? Because capacitor was already charged when this was allowing the flow of current. So during that time, capacitor wants to discharge, right? But we can see here it is connected to the input terminal of the operational amplifier, and we know operational amplifier has very high input impedance. It means high impedance means there is no scope for the flow of current toward this side. So in this case, the capacitor won't be able to discharge, and it will hold whatever voltage will be stored in it, whatever potential will be stored in it. So the whatever sample was taken during this time when the current was flowing, that sample will be holded in the capacitor, and the same is applied here, right? Right. Here I am saying that the same amount of the sample will be holded by the capacitor, but in reality the capacitor will discharge very slowly, right? So we are ignoring that. We are taking the ideal situation that the capacitor is going to hold the entire voltage, right? Then after, what will happen? Again, then the next cycle, this cycle will come, right? Then the next positive cycle will come, again this switch, this MOSFET will get closed, and now again the signal that was coming from here, now it is again start flowing toward this side. So when again the signal start flowing toward this side, now again the capacitor want to charge according to that signal, right? Whatever the signal, whether it is rising or it is falling, so according to that the capacitor will start charging again. So again the sample will be taken. So again when the next cycle, that is zero or negative cycle come, again this switch will become open, and this capacitor will hold the sample. So in this way we can say what I said here, that it is sample and hold. So we can say here it is taking the sample and then holding this, this part of this circuit, that is n channel enhancement MOSFET. It is taking the samples and this capacitor is holding these samples, right? And then these samples are applied across this operational amplifier, and I told you that this op-amp is acting like a voltage follower. Whatever voltage will be appearing here, the same will appear here at the output that is connected with the oscilloscope, CRO, right? So we can see the waveform, how this sample is taken and how it is holded. So this process will continue. So this is the way of working this sample and hold circuit, right? I can show you the waveform of this sample and hold circuit. The things will become even more clear when you will see. Right, you can see here, right? How the this is red is input signal, right? You can see, and blue is the output waveform. So you can see here, red signal is basically a sine wave that is continuously varying, right? You can see here, but you can see, for example, during this period of time, right? Can draw it in this way also. Actually, this is the right. Then this is again, this one, right? This is in this way. So you can see from here, although this in this waveform there is some problem, but it is easy to understand from this waveform that how this input signal is getting sampled. I'm showing you one more waveform here. So you can see from this waveform, I'm showing you this waveform. This is the waveform, right? That is, more clearer than the earlier waveform. Here you can see it is the input waveform. It is varying with time. This is the MOSFET. Now you can see during this time the MOSFET will be open, right? During this time the MOSFET will be open, right? And this was the input waveform, right? This red one. So when the MOSFET is open, right, you can see the output waveform, right? Means charging and discharging, charging of the capacitor. When this is open, the capacitor want to charge in this way, and at this point the now MOSFET is off. So the capacitor, whatever value of the voltage is here, it will be holded for this period of time, right? Then after again the MOSFET is open, right, on, right? Then again it will the voltage across capacitor will follow the input signal, right? In this way, once again when it is off, it is again taking the sample. So you can see here that how the samples are taken. Actually this was shown there in that we were discussing how this waveform input and output are drawn, right? So I think the thing is very clear now how this is taking the samples, right? MOSFET on, MOSFET off, and this is the holding time, holding period, and this is the sampling period. Sampling period, holding, right? So in this way we can take the samples of the input waveform, and we can convert a given waveform into corresponding its a kind of digital format. I'm saying kind of digital because we have to further process it in order to convert it into a fully digital format, right? So this is the way how this circuit will work. I will show you a simulation that will makes the things even more clear. Right, you can see a simulation of a sample and hold circuit. right? So you can see this is the circuit, this is the oscilloscope. As I told you, we have applied all these values here. So when you will see the waveform, you can see here, right? We have put the different values of capacitors, supply voltages, right? And then you can see here, right? You can see here whatever waveform we have seen. So this is the input. Red waveform is input and blue is output. So you can see how the samples are being taken, right? This simulation is shown on a simulation package multisim, right? So you can change the values of if of the input signal capacitor, and you can see what changes we are seeing there in the output waveform, right? The samples that are taken, right? You can see here. The different waveforms we can see by changing the values of the input signal, value of the capacitor, value of the resistors. So this makes the things even more clearer, right? So this is about the waveform, right? So I'm hopeful that this working of sample and hold circuit is very clear. So this is all about sample and hold circuit. If I talk about the application, I have already told you that the main application of this is for analog to digital and digital to analog conversions, right? So thank you very much.